Hi everybody, Mr. Bozaday here. Right now we're going to figure out the equation for work. Let's start. We're basically going to just come up with the equation just by understanding and thinking about the definition of work. So work is the energy transferred into or out of a system by an external force, right? Let's be careful with this. Work is it's an amount of energy, right? It's not a force. Okay, the force transfers the energy, but the work is the energy, right? So, and that's why when we do our LOL diagrams and we go like this and we say that's like work of force push, for example, we say energy is transferred in, like the work transfers energy in. Or if we go like this and we do like work of force friction, we put a block there to represent energy transferred out. Okay, so work is the transfer of energy. Well, since it's the transfer of energy, you should guess that the units are joules, right? Because it's transferring energy, joules of energy. We know that we can write joules as a capital J, but really joules, if you remember Miss Rona's video, are Newton meters, Newtons times meters. So if I were to ask you to take a guess at what you think the equation for work might be, hint, 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 Newtons times meters, you'd be right if you guessed work equals force times distance, because we measure force in newtons and distance in meters. Now, it is a touch more complicated than that. It's actually force parallel times distance. And what that means is that means the component of the force that is parallel to the displacement. That's what that means, okay? We can also write that as force times displacement times cosine theta. Sometimes you'll see it written like that. I typically don't write it that way because sometimes people do not do a good job of figuring out what theta to use, because when you look at a triangle, you might use one angle or the other angle, and sometimes people struggle with that. But when people find the component of force that's parallel to the displacement, usually they do well with that. So I'm going to use this equation. Here we go. So what we'll do is we'll look at 1, 2, 3 examples to help you kind of get a better understanding of work here. All right, so in example 1, box moves 8 meters forward due to a 12 Newton force that's applied at an angle of 15 degrees above the horizontal. An identical box, so that's this first one that we just described, an identical box, this one over here, is pulled with the same force over the same distance, but the force is horizontal. There's no friction in either case. Will each box be moving the same speed? Come up with an equation to calculate the work done. Okay, so we've got our equation. I've gotten it. We've looked at it. We got it right there. And so here we go. For this guy, what we know is this is 12 newtons right here. And we know that this angle in here is 15 degrees, okay? 15 degrees. And so if I'm going to do work equals force parallel times displacement, the displacement is that direction. So we need the x component of the force, of the pull force, so that we can multiply that by the displacement, because you can easily see that those two are parallel to each other. So let's start by finding the x component of the pull force. So that's going to be cosine, because that's adjacent to the angle. So we're going to do the hypotenuse, which is 12 newtons, times cosine of the angle, and the angle is 15 degrees. And that's going to give us our x component of force, which is 11.59 newtons. Now to find the work, we just multiply the 11.59 times the displacement. And are we told how far? Yes, we're told that it goes 8 meters, okay? So then we can go, so work equals 11.59 newtons times 8 meters. And when you plug that in your calculator, you get 92.7, and you could write that as Newton meters, but typically we write it as joules, right? Because it's the transfer of energy, all right? So on the other hand, if the 12 newtons was perfectly horizontal, then we don't need to find any components, right? It's all parallel to the displacement, and the displacement's still 8 meters. So if we want to find the work for that guy, we go work equals force parallel times displacement, but we've already got the full 12 newtons is already parallel, so we're going to say work equals 12 newtons times 8 meters. And so that's going to give us, 96 newtons, right? Yeah, 96, Newton meters, or like I said before, 96 joules of energy is transferred. That's the work, okay? So important note about the work equation, as we mentioned right here, the important note is just that what it really is force parallel times displacement, right? Work is, got to get that parallel component. All right, let's take a look at the second example here. A person pushes a box horizontally with a force of 5 newtons, but due to static friction, the box doesn't budge. How much work is being done on the box? Okay, so let's see. Work equals force parallel times displacement. So our force is 5 newtons, and we're told that it's horizontal. And the displacement is, let's see, the box doesn't budge, so it doesn't move, so the displacement is 0 meters. So there's 0 work done. So the important note from this example is that the object needs to move. For work to be done, the object needs to move. Object needs to move. Okay. All right, let's take a look at the third and final example. A person exerts a horizontal force of 20 newtons to push a box 8 meters forward at a constant velocity. Okay. Calculate the work done by force push. Calculate the work done by force friction. Okay, so since it's a constant velocity, we know that our free body diagram for the box is going to look like this. We're going to have force gravity, force normal, and those will be balanced. And then we've got like force push and then force friction, and those will also be balanced. So what that means is that if the person's pushing with 20 newtons of force, if this is 20 newtons of force, then friction is also 20 newtons of force. All right, so calculate the work done by force push. It goes 8 meters, so it's work done by force push equals force parallel times displacement. And so that is 20 newtons times 8 meters. So that's going to be 160 joules, 160 joules, right? And the work done by force friction, well, it's going to be like the same thing, right? Because it's also 20 newtons. So work of force friction equals, maybe I can move this out of the way, give us a little more space. Work of force friction equals force parallel times displacement. Now here's the thing. The displacement points to the right, right? So the displacement points to the right, but the force of friction points to the left. And so what that means is they're like what we might call anti-parallel, right? They're parallel, but they point opposite directions. So we might consider calling that anti-parallel. And when that happens, well, it means that the work is going to be negative. So what we get is we put a negative sign in front of that, and then we do, 20 newtons times 8 meters, and then we get not 160, but negative 160 joules is the work done by force friction. And so an important note about the work equation is that positive work adds energy to the system, while negative work removes energy from the system. Okay, and there you go. So those are all the notes that you need about work. Make sure you get these. I will email them to you, and I'll see you later. Thanks.